Types of box girders in bridges. Based on number of cells, there is single cell box girder which has one hollow core, which is most common and used in moderate spans, and which is easier to construct and maintain. Maintenance is easy in this. And next is multi-cell box girder, which has multiple number of cells. 2 to 5 multiple cells are there always. 2 or more hollow cores, used for longer spans and wider decks. Means the deck is wide. For wider decks, these are used, and this possesses high torsional rigidity. Next is based on shape and cross section. First one is rectangular box girder, which is simple geometry, often used in buildings or short bridges. Next is trapezoidal box girder, which is sloped side walls, more aerodynamic, better torsional resistance, and common in highways and railway bridges. Next is circular or elliptical box girders, which is rare in bridges, but sometimes used in special structures or aesthetic architecture. Next one is based on material. Concrete box girder, which is cast in situ or precast, usually pre-stressed or post-tensioned, suitable for medium to longer spans. Next is steel box girder, used for very long spans and curved alignments, lighter but more complex to fabricate, often used in cable stayed and suspension bridges. Next is composite box girder. Steel box girder combined with concrete deck slab. Combines the advantage of both materials, efficient for longer spans and heavier traffic. If traffic is heavy and long spans, composite box girder is helpful for us. Next is based on construction methods. Cast in situ box girders, built directly on site, more flexibility in shape, suitable when precast transport is difficult. Next is precast box girders, made in factories and transported. Faster construction, requires lifting equipments like crane and transportation access, better transportation access. Next is segmental box girders, constructed in segments, either precast or in situ, ideal for long spans, balanced cantilever construction. There are many applications commonly: flyovers, metro viaducts, cable stayed bridges as deck slabs, railway bridges, balanced cantilever bridges. These are all uses this segmental box girders. Here you can see there is a top slab which carry mainly vehicular loads. Then bottom slab balances compression, takes dead load. The webs usually take shear forces. The two webs usually take shear forces. Vertical bolts connecting slabs, and the voids inside that cells inside that reduces dead weight, enables post-tensioning ducts for cables. Post-tensioning cables ducts inside that. It carries that. Also, it reduces dead weight. Diaphragms, provided the supports at intervals for transverse distribution and stability. And tendons or cables which are applied on pre-stressed concrete. Pre-stressing elements inside ducts for strength and crack control. These are the important IRC codes for Indian Roads Congress codes for box girders. IRC 6 for loads and general design principles, IRC 112 limit state design, IRC 18 pre-stressed concrete bridge design, IRC 21 working stress design, IRC 24 composite bridge design, IRC 83 bearing. Most important codes for bearings is IRC 83 specifies the bearings for that, and IRC segmental bridge design is proposed in IRC 87. IRC SP 65 and IRC SP 71 both gives segmental box girder bridges and elevated metro structures for box girders. Next is why box girders are structurally efficient, which is compared to eye girder. Compared to eye girders, we can see that the moment of inertia is comparable or higher, and the torsional resistance is excellent, and the warping is low, and the shear distribution is uniform. For the eye girders, more evenly spread, and the stability is high in box girders compared to the eye girders, which implies closed sections avoid local buckling. Stability is high, somewhat high in box girders. Anyhow, both are used commonly in modern construction practices. Both are used thoroughly in constructions. Box girders and eye girders. Both are commonly used. Thank you for listening. Please like, share, and subscribe.